On Friday, we spoke about mean field theory. Alright, so mean field theory we did as a kind of a lattice exercise where we basically took the simplest model, which actually has a base transition. So it's a nearest neighbor square lattice 2D Ising model. And so the 2D Ising model. And we said we're going to focus upon a particular spin here. And we're going to ask ourselves what its partition function is going to be if we replace all the nearest neighbor spins by their average values. Okay, so we said the average value was m, so m. And this led us to an equation, a self-consistency condition, which said that the average value of the spin must be m, and that must also be this. And by looking for non-trivial solutions of this, we were able to find out the critical point, which was basically Tc was 4 times j. And then we were also able to find the behavior near the critical point. Okay, what the behavior was. Several different kinds of things. So we figured out that m behaves like Tc minus t to the 1/2, okay, for t less than Tc. So this gives you the critical exponent beta, which is 1/2, right? We also figured out that dm by dh at h equal to 0 goes like 1 over t minus tc for t bigger than tc. This tells us that the critical exponent gamma is equal to 1, because gamma is the power with which the susceptibility diverges as you approach the critical point from above. Okay? And let's see, maybe we can figure out another critical exponent as well. Right. So we figured out that if you're sitting exactly at Tc, and then you ask yourself, how does m behave as a function of h? We figured out that it behaves like the 1/3 power of h. So this tells you that the critical exponent delta is equal to 0. Okay, there are a couple of other critical exponents that we will define very shortly. But for that, it's better to go to this next version of mean field theory that I basically introduced last time. Okay, so this is roughly what we covered last time. Any questions about any of that stuff?
Can we determine this derivative for t is less than tc?
Well,
Because
it would be less than Tc.
the only thing we assumed was that the free energy could be written as, expanded in m square. So that is true on both the ends, right?
Let's see, you can certainly expand around the average value. Right? You could do that. Yeah, you could certainly do that. And then you can ask how much the magnetic field changes. So the susceptibility should actually diverge from both ends, on both sides. Okay, and yeah, several other exponents are also like that. But you have to be sure to cancel out the average value.
But so the exponents can be in principle different.
In principle, they could be different, but in reality, they're always the same. Okay? All right? Other questions?
Yeah, so how do we calculate subleading so corrections beyond mean field?
Corrections beyond mean field. Right. So we're going to get to that. So that's part of what this class is going to be about.
But
If we get there.
Can effective field theory handle it, or do you have to do the real microscopic theory?
No. You can always do everything as far as the critical, point is concerned. If it's a second order phase transition, it has scale invariance. So everything really depends only on long distance scale. So the microscopic theory doesn't matter.
Effective field theory.
So you can always do it in terms of effective theory, but the question is whether mean field theory by itself is correct or you have to do something beyond mean field. Okay? And typically the answer is in 3 dimensions, you always have to go beyond mean field. And we will see that very shortly.
Even in 2 dimensions, right? Even this one.
Anything below 4 dimensions of a standard field theory, we'll have to go beyond mean field. Above 4 dimensions, mean field theory is actually good enough.
Because of the irrelevant.
Yeah.
Why is irrelevant?
Okay? Good? So what was this? So we introduced a different theory which I called a coarse-grained theory. Coarse-grained, or sometimes known as an effective theory. So what does this effective theory have? Well, it has all the symmetries of the original theory. Okay? And it has everything that you need from mean field theory in order to get whatever we've gotten so far. And in addition, it has a couple of other things that allow us to get all the other exponents. So what is this effective theory? So let me say that now I'm going to promote this m. This m used to be a constant, right? So here I'm going to promote it to a field that varies slowly. When I say slowly, I mean slowly on the scale of the lattice. Okay, so remember, this is critical behavior. So we're not really interested in precisely what is happening on the scale of the lattice. Okay, so all the important fluctuations are going to be fluctuations that happen at very long distance scales. Okay? So to let it vary slowly is good enough. All right. So now locally, if I look at some particular region in which phi doesn't vary too much, let's say phi is a constant, then it should really reduce back to this. Right? So what was it that we really used of this m? So remember, in all of this, we really used only the expansion of the standard hyperbolic to third order, right? The linear power and the third power. That's all we used. So somehow we should get the same result by minimizing whatever this effective theory is. So therefore, I can write something that looks like a times t minus tc over 2 phi squared of x plus some lambda over 4 right to the 4 of x. Okay, and I can write down some dot 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 here, but near the critical point, that dot 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 will not matter. At least as far as mean field theory is concerned. Okay? Maybe when we go beyond mean field theory, we'll realize that we have to include those. Okay? But actually, as it happens, we won't. But it's possible. Okay. So this part, as you can tell, as soon as I reduce t below tc, this part becomes negative. And then if I try to minimize this free energy with respect to phi, I'll get back exactly all those things. Okay? So this is the part we've already done so far. Next, I'm going to introduce something else, which tells you, so let me first write it down. This basically says that phi likes to remain constant. It doesn't like to change. Why is that? That is building in the ferromagnetic coupling of this original model. Right? The ferromagnetic coupling says that if the spins are all lined up, then it costs a lot of energy to flip a spin. Okay, so it costs a lot of energy to change this phi. Okay? So this phi has a certain stiffness. Okay?
Sorry.
Yeah.
That phi.
Yeah.
Here we are taking the continuum limit.
Yeah.
So without the continuum limit, it is something that at two lattice position, the difference is phi, difference in phi by the lattice spacing. That is what the square of this is coming to be, that gradient phi.
Yeah. Yeah.
So how is this coming in the Hamiltonian original Hamiltonian?
So remember that the original energy functional, right?
Yes.
So the energy functional was really something that looks like minus j sum over nearest neighbors SISJ, right?
Yes.
Let me write it a bit more explicitly. I will write it as minus j sum over position vectors and what I will call direction vectors. Okay, so at every position I have two different directions in which the neighbors are, right? So let me write it as S of R times S of R plus VI, okay? And on the square lattice there are two of these directions. So you agree that this is exactly the same as what I wrote before. But now I can use a certain property of this S, which is that S squared is 1.
S squared is 1.
Right? Because S is only plus or minus 1. So I can rewrite this as something that looks like J over 2, the sum of R and Ti, S of R plus Ti minus S of R squared. So the cross term will be exactly this.
Yes, the square terms are 1.
The square terms are 1. So I subtract minus j times the sum over r and I of 1, and that's just some constant.
Okay.
It doesn't depend on the configuration.
Okay. Now we are just multiplying a square and a square here, and that a square converts to that delta d2x.
This is like the gradient or the lattice. Okay, so this is like the gradient square. Okay? Fine. So that's the way you should think about it.
Okay.
Alright?
And so that j sum over 1, that term you are ignoring because it's a constant contribution.
So it doesn't depend on the configuration.
Depends on the
So therefore, when I divide by the partition function, if I want to take some correlation function, it won't matter.
It just factored out outside.
It's just completely factored.
Are there like exact field transformations which can really give the Lindau-Ginsburg theory?
Yeah, you can. You can. But that's not really the correct way to think about it. Okay, you can certainly do an exact transformation and get this plus, millions of other terms.
Yeah.
But that is not the way to think about it. The way to think about it is that you have taken some region and you've added up all the spins in that region. Okay? The sum of all those spins in that region up to some constant factor, which we don't know quite yet. Okay, some factor that scales it with the size of the region over which you're taking an average. Okay? That is what you should really think of as phi of x. That is why this word here, coarse grain. So you're taking some regions and you're making them into slowly varying fields. Okay? So that's how you should really think about it. That's how this guy that used to be plus or minus 1 has become a continuous field. Okay? The one thing that it still remembers back from when it was a discrete object is the fact that if I change all the spins to minus of themselves, the energy function remains invariant. Okay? And that symmetry is still present here, as long as I don't put an external field. Okay? Now if I put an external field, of course there will be some term here that looks like that, right, in the energy functional, and now I have to integrate this over all the sides of my lattice, so I'll be using the sum integral and sum and so on interchangeably.